Hello, everyone. So today we're going to be discussing chapter one. And so within that, things we're going to cover. So today's objectives. So we're going to talk a little bit about mechanics and statics. We're going to go over units, how to round your answers. Basically, if you have things that you should already know, things that you possibly have covered in other courses like math, algebra. Obviously, you're going to round up or you'll round down with depending on how many significant digits you have. And then just give you some tips on problem solving. So what is mechanics? As stated in your book, mechanics is a branch of physical sciences that is concerned with the state of rest or motion of bodies that are subjected to action or of forces. So in other words, it's the study of a body being acted upon by forces, mechanics. And when you think about a body, right, it is anything that has a collection of matter, right? We call it a thing, we call it a body. If you think about your body and how your body functions as forces or acting upon it, which is gravity for the most part, or even if you are hit by something, how does your body respond? It'll put your body in motion, or it'll keep your body at rest, right? When you think about gravitational forces being on your body, it keeps your body at rest on the earth, right? As the earth is spinning, you don't feel the rotation of the earth because the gravitational force on your body keeps it at rest, which brings you into statics. And statics, which is, I know I'm getting ahead of myself, but as you go into branches of statics, or even the branches of mechanics, you have rigid bodies, you have deformable bodies, and you also have fluids. In rigid bodies, you have are divided in two areas, which is statics and dynamics. And statics, bringing me back to statics, because I was getting ahead of myself. Statics deals with the equilibrium of bodies. That is, those that are either at rest or move with a constant velocity. Now, I know you're probably wondering, what does that actually mean? Well, you think about a body and you think about a force acting on the body, just as I was discussing earlier. Force acting on my actual body, gravitational force, is keeping me at rest on the earth while it is moving, which is statics. So I have a force that is keeping me at rest on the earth, grounded, that is, on the earth, while at the same time, the earth is acting on my body from beneath me, right? That's keeping me from going through the earth, right? I'll never get too heavy for the earth. Now, you can imagine somebody that heavy, right? As they walk, they sink through the earth. Now, that would be pretty crazy. Now, there probably are some areas on the earth, right, that you could walk on and you would probably sink, such as sand. But notice you don't sink all the way through the sand. You go down a bit, right? But not all the way through. Though there are some sands that, you will go all the way through, which is possibly liquefied, right? But anywho, moving right along. So you think about the branches of mechanics divided into rigid bodies, right? Deformable bodies and fluids. You have bodies that are deformable. When you think about a deformable body, you think about something that is spongy, right? Like rubber, something like rubber. You can kind of deform it, change the shape of it, mold it. Putty would be another deformable body. Obviously, you should know a rigid body, like our bodies are more or less rigid bodies, even though we can change the form of it, but not for the most part, it stays the same shape. So you possibly have, maybe our muscle would be a deformable body, but then our bones would be a rigid portion of our body. But something more concrete would be like a rock, like a solid rock. That would be a rigid body. A car would be a rigid body. If you think about something that is more mechanical, your phone, and then fluids obviously would be more simple, would be gas and then liquid. Now, liquids are incompressible, which even though that in physics, you should probably learn that incompressible and compressible fluids, you have gas, which is compressible, right? So if you compress gas, it makes the molecules smaller, and they continue to get smaller, and then they begin to multiply, right? And then you as you compress it, it begins to multiply, becomes smaller, and then more of them form, right? Whereas a fluid looked at as incompressible because a fluid is liquefied. So most of it more likely it takes the shape of whatever is trying to compress it, right? But you can actually compress fluid. It's just the compressibility of a fluid is so much smaller than a gas, right? Which is why we say it's incompressible. But if you continue to press and press and press and press on a fluid, right, it will press. Like if you think about the ocean and you think about wind, right? If you think about amount of pressure or wind on the earth or on the ocean, and then it's up against the earth, and you continue to press and press and press and press, it will press, right? It will compress eventually with enough force. You probably haven't been taught that, but in physics, they should have touched on it slightly. But in engineering, we do understand. It's like a different mindset from an engineering standpoint that, it is compressible. It's just the compressibility factor is so small and minor that it would take an extreme amount of force to compress a liquid. All right, so moving right along. Units of measure, right? Think about the force acting on that object. You have, well, even before we get to that. So yeah, just stay there. Force is acting on that object, right? You have different units when it comes to, even units of measure when it comes to forces, time, mass, and length. And the reason why we bring up length, mass, and time is because you're going to use length, mass, and time to come up to solve for the force, right? But when you think about the units of measure of the force, you have different units of measure, and we'll get into Newton's law just in a second. But when you get to the units of measure, you have the international customary units, and then you have the international, you have the US customary units, right? What we use, such as pounds, slugs, things of that nature. And then you have the international system, SI units, which is newtons and kilograms. Now in the US, we're special. So, Canada also uses pounds and slugs in addition to international system units, which is newtons and kilograms. But Canada is a special case where they use both. We don't. We only use US customary units. All right. And when you think about the force and the measurement of a force, so the measurement for US would be a pound, which you should know. And then for SI, it's a newton. And going back to forces, though, Newton came up with 3 laws when it came to forces, or forces acting on an object, right? Newton's first law: a particle originally at rest or moving in a straight line will constantly, with a constant velocity, tends to remain in this equilibrium state. So an object that is at rest will remain at rest, right? It will remain at rest. Or an object that is moving will remain in that state of movement. It won't change. The velocity won't change. The acceleration won't change. It'll be constant. It's either constant motion or it is constantly at rest. An object will remain in either one of those states. That is Newton's first law. All right, then the second law, which you should already know if you've had physics or intro to engineering. Second law: a particle acted upon by an unbalanced force, or an object acted on by an unbalanced force experiences an acceleration that has the same direction as the force and a magnitude that is directly proportional to the force. So in other words, an unbalanced force. So like I was saying about a person being so heavy walking upon the ground that they would tend to sink, right? Their weight on the ground would be unbalanced because the gravitational force on my body and the ground, we call it the ground to sink, would be an unbalanced force versus an equal and opposite force, right? That would allow you to remain or would allow the earth to remain in the same position as you walk upon it, right? It wouldn't sink. And I know that probably isn't the best, what you would call the best example of that. But just giving you the example of a person because we were talking about a body and things of that nature. But things you've already know, right? You should already know at this point, but just wanted to go over it again, reiterating this as we cover this portion of statics. But anyway, so the second law is force is equal to mass times acceleration. So an object will accelerate with unbalanced forces on it. And then Newton's third law is the mutual forces of action and reaction between two particles. In other words, for every action, there is a reaction. And as I just took note from another instructor is because the action is the force. So for every action, there is an equal and opposite reaction. For every force, there is an equal and opposite force, right? Which goes back to the first law, which is the reason why things remain at rest. But when Newton's third law, you think about if you punch something or you hit something with an amount of force that hit the amount that you hit the object, right? With that amount of force, that object is also returning that same amount of force onto your hand. So your hand will receive the force that you exerted onto the object, right? So you think about punching somebody as hard as you can. Well, your hand is also receiving that same amount of force that you punched the other person with. So just keep that in mind when you punch people. So don't punch people, right? Unless you're a boxer and you get paid to do it, or MMA fighter or whatever. Anyways, moving right along. Unit systems, as we discussed, we went over that. And so in your book, we'll probably do some conversions. So you'll be converting from Newton pounds and things of that nature. Then you got your common conversion factors. You think about, again, significant digits. So you keep that in mind. So if you go, can you convert a force value of 47 pounds to into SI units? Yes. So you would actually solve that, and then the answer is 209.06. And so for your sake, we would say 209 newtons, right? Because you're going to round up or down, right? So you just go ahead and round down on that particular problem. And then the other things we will not go over. So if you think about numerical calculations, must have dimensional homogeneity or homogeneity, however you prefer to say it. But what does that mean? That means when you are solving a problem, you need to have the same units, right? For every factor that you are using or working with, right? So if you are solving a problem and you're needing the acceleration, and you have a force in newtons, and you have a mass in pounds, right? Because in US customary units, you can have a mass in pounds mass, right? So you would have to convert that pounds mass to kilograms in order for you to solve for the acceleration in meters, right? And vice versa, right? So you want to make sure all of your units are homogeneous or homogeneous, all right? And also, this is something key too. So whenever you're solving a problem, make sure you keep the same amount of significant digits that you start out with. So if you start out with 3 significant digits, make sure when you're calculating one thing to get to the other thing, or one unit or one measurement, such as if you looking for acceleration and then you have to convert pounds mass to kilograms, and you do your solving for your conversion for transferring pounds mass to kilograms. Make sure if you started out with 3 significant digits, make sure you keep those 3 significant digits as you convert that. And then when you use that conversion, use the same 3 significant digits to solve for your acceleration. You plug that back into your problem. All right, and we're now going to do the concept quiz. So problem solving strategy. So interpret, read carefully, and determine what is given and what is to be found. Deliberate, ask if not clear. If necessary, make assumptions, engineering assumptions, and indicate them. Plan, think about your major steps or roadmap that will take to solve a given problem. Think about alternative creative solutions and choose the best one. And then lastly, execute. Carry out your steps. Use appropriate diagrams, equations, estimate your answers, avoid simple calculation mistakes. So when you think about solving a problem, you always think about first drawing your free body diagram and indicating how the forces are acting on the object, the direction, right? And any other thing that you may can draw out, just so you always start with a free body diagram when solving engineering problems, which you should know by now from physics and intro to engineering. So this is my time. We will see you again for chapter 2. Thank you.